So, now we should be ready to dig in deeper to thermodynamics and do some, or at least discuss some more non-trivial stuff that will help us understand that there's more in this than in the simple examples that we only scratched. Second principle of thermodynamics, it's one of the controversial things in science, or was. It took some decades, if not a century, to be formulated properly. It has many names. Second law of thermodynamics, Clausius-Duhem inequality. So there were many people involved in finding it out. In our formalism, it can be written in the same structure as conservation laws, but it's an inequality. It is not satisfied as equation, at least not all times. So it has a conserved sort of, instead of conserved quantity, there's a quantity S, which is called entropy, and the change of entropy is bigger than sort of the source term of entropy, which is the energy source divided by absolute temperature, and the flow term of entropy, which is flow term of energy divided by temperature. So this is so in general this is not an equation. So there are processes where this works as an equation, and there are processes where this is a strict inequality. And if this has to be valid all the time, whenever it's an inequality, something irreversible happens. So it can't be undone, because undoing would sort of would violate this condition. So the entropy, once entropy increases, it can't decrease back in the same way. And this has very fundamental consequences. It has implications. It limits the possibilities to write material laws and to write models. It says essentially that energy is moving from hot to cold. It says that the friction always works against the direction of movement, and so on. So it's in some sense it gives not sense but direction to the universe. I guess it has something to do with defining the order of time and so on. But that goes already rather deep. We don't go that far. What are the consequences and how they come up from the second principle of thermodynamics? So if you simplify or modify simplify the conservation or the Clausius-Duhem inequality using conservation of mass, conservation of energy, because again the components of conservation of energy were visible in Clausius-Duhem inequality, so it's sort of natural that it can be played around. We will get, among others, this form, so where there is some time-dependent term, change of entropy, change and change of internal energy normalized by temperature. And then two terms remain. One is related to forces and velocity, and one is to heat flux and gradient of temperature. And now, assuming that we can have arbitrary time dependencies, so this can be, for example, 0. So if you have a stationary situation, only these remain. If velocity is 0, this means that in stationary system, no velocity, q times gradient of t must be positive. This tells that heat flux must be from hot to cold. And likewise, if you have temperature constant and play around with velocities, if we are dealing with fluids where tau was proportional to gradient of velocity, this tells that the viscosity coefficient, that is the coefficient of proportionality, it must be positive, which means that basically the viscosity is damping down the movement, it's moving mechanical energy to heat and so on. Basically that friction is moving mechanical energy to heat. These are found from here. What is a bit deeper hidden in the law, but still a rather simple mathematical exercise, is that if we have 5 thermodynamical quantities that are mentioned in these laws, so density, pressure, temperature, internal energy, and entropy. If we know one of these as function of 2 others, this will be called a state equation. So having such a law, once this is done, the rest will be resolved. So with one law we can fix sort of 5 quantities. So that will help us in closing the systems. You might know from high school physics, for example, the state equation of ideal gas, which is PV equals nRT, at least in my physics book years ago. Basically, it's a law between pressure, density, and temperature. Once this is fixed, so once we fix this coefficient, we have fixed also the formulas for internal energy, formulas for entropy. And that will then lead us further in closing the models. Let's discuss briefly how the atmosphere is behaving. So we know that the pressure, density, and temperature vary in the atmosphere as a function of altitude. What is behind this? Why it is so? And what can we sort of derive from basic principles? In thermodynamics, there's a concept called free energy that we denote here by A, which is basically, if we count it from here, it's the difference of internal energy and product of temperature and entropy. So it's basically the part of internal energy that is not just basic heat, that can be made to work. It's free. It's convertible in some sense. So if we write free energy as a function of density and temperature, or inverse of density actually, then we can also show that the pressure is a derivative of this function with respect to density, and entropy is the derivative with respect to temperature. For ideal gas, we can formulate this type of free energy. This will lead to known formulas, well-known formulas for internal energy and also the dependence of pressure and density. That's something you can work out on your own. This is simple derivation basically. Now we have to start assuming things. If you assume that entropy is constant with respect to altitude, that means that whenever air is moving up and down, it's moving in a reversible way, so it doesn't make anything irreversible like start to rain or something. So this is in large it's a non-realistic assumption, but helps to work around, or helps to elaborate this a bit. So entropy is constant, so we can compute expression for entropy, make it constant. It will give us proportionality between temperature and density. And once this is done, we get proportionality between pressure and density with constants that appear from this law. And once we have pressure as a function of density, we can come back to conservation of momentum, which is simplified as a differential equation for pressure, which is now a differential equation for density, involving density and the gravitational field. Gravitational field behaves like 1 over altitude squared, and we can solve this and get the decreasing function of altitude for density and then for pressure and temperature. So we get basically profiles for all these variables where we were interested. Of course, these qualitatively behave in large as the actuals, but not fully, because the assumptions are not realistic. So the real atmosphere is not an ideal gas, and it doesn't also behave as irreversible isentropic. But to get an idea that you can use these relationships to derive at least qualitatively meaningful formulas of more complex situations. But that about thermodynamics. So now it's time to summarize. Now we should know something about continuum mechanical models. They are all built on top of conservation laws and on top of conserved quantities that are well-known standard. Unfortunately, they are, in some cases, they are considered so well-known that some authors even ignore them. I have seen some applied papers where the elaborations of models where the conservation laws are never mentioned explicitly, and actually the full model is never written out. There are big elaborations of material laws, complex fittings to measurements and so on, but the models are never closed. So you may end up to situations where you are asked, for example, to implement a model given in some paper, and you will never find out what is the full system of equations that is resolvable because people omit material laws like conservation of mass, conservation of momentum, and focus only on particular source terms, flow terms, and so on. Or particular free energy for the material. What you should be aware of is what type of models to expect from sort of raw continuum mechanical modeling. If nothing fancy is done, the continuum mechanical models, typically they have two special derivatives, because one comes from the actual conservation law, which is the divergence coming from the boundary term of the flux or the flow term, and other comes from the material law related to the flow term. Like heat flow is dependent on the gradient of temperature, stress is dependent on gradient of displacement or velocity, and so on. So typically two special derivatives. Exception is when there is no flow term, when heat conduction is negligible, when viscosity is negligible. We get the systems that are called systems of conservation laws, where only the one special derivative from the conservation law is present. Typically, this is in high-speed aerodynamics, Euler flows, and so on. And these are models of their own kind, have their own peculiarities. As for time, many models have typically one time derivative that comes from the conservation law, and that applies like to heat equation. And this type of models typically smoothen in time. In solid mechanics, you end up to models that have two time derivatives because the displacement and gradient of displacement, it appears in the model as a primary unknown and not velocity, and that brings another derivative. So to get to the velocity you need another derivative, and you have one more time derivative before you get to the equation. And this type of equations with two time derivatives, two space derivatives, they don't also have smoothing behavior. They are wave-like. So that's why you end up to following oscillations and having solutions that don't smooth up in time. These are, in some sense, more challenging to solve properly because there's non-trivial thing going on forever, and hence you have to be able to simulate forever, and you can't allow any errors to accumulate, because eventually they will blow up your system. The dissipative systems are smoothing systems that will smooth out the differences in time. They are sort of easier. They also smooth out small errors in time and are nicer to work with. So this was a short introduction to the structure of continuum mechanical models, and I guess you will be elaborating these in the exercises. Thank you for your attention.